Hola, buenas tardes. Ya vamos a empezar. Ok, 5 minutos más. Muchos van a verla desde su casa. Orlando se fue a su casa. Es vía streaming. Sí. Se fue corriendo. Que sean tres. Es que empezar ¿cómo así los tigres? Buenas tardes. El título de esta conferencia es Full Scale Experiments in a Modern Tall Building. El monitoreo de estructuras se ha convertido en una herramienta importante para entender su comportamiento cuando es sujeta a cargas dinámicas. El análisis de los datos recopilados sirve para evaluar el desempeño e identificar el daño o deterioro de las estructuras. La conferencista de hoy tiene una enorme experiencia en este campo. Es especialista en ingeniería sísmica, ingeniería sismológica, en mecánica y en procesamiento de señales. Los temas que domina tienen que ver con la identificación de sistemas estructurales y monitoreo de su salud, con movimientos fuertes de tierra, ruido urbano y sus efectos en las construcciones, evaluación probabilista de riesgo sísmico y pérdidas, la propagación de ondas sísmicas en suelos y estructuras, interacción suelo-estructura, modelado de campo cercano de tsunamis, etc. Ella ha trabajado como consultora sobre movimientos fuertes de tierra, evaluación de riesgo y procesamiento de datos sísmicos para agencias gubernamentales, la industria del petróleo, de desarrolladores, de firmas consultoras y de bufetes de abogados. Es profesora en la Universidad de Tianjin, China, y es profesora investigadora adjunta en la Universidad del Sur de California. Las dejo con la profesora María Todorovska. Welcome.
Okay. Thank you, Marta. Thank you, everyone, for coming. So as I spent most of my life, actually adult life and career in Los Angeles at the University of Southern California, where I got my degrees and where I worked as a research faculty, and I still have an appointment there. But in the last 6 years, this is 7th year, I got an offer to work in China that I couldn't resist. And what I'm presenting today is the reason, actually, that brought me there. So what I will present is what I've done over there. Over there, I founded the laboratory for full-scale observation and simulation of earthquake response. Okay, so let me see. So first, I'm going to introduce the seismic monitoring project that I installed there, and then present results of different topics we've worked on using this data, or that were motivated by this full-scale observation site, such as identification of natural frequencies and wave velocities from microtremors, effects of weather on the natural frequency of vibration, observed and predicted effects, observed response during earthquakes. I'll just show a few animations. Then observed rotations during earthquakes, focusing on point versus chord rotations, and then digital twin that we made, which considers soil, piles, basement structure interaction. It's a finite element model in OpenSys. And then I will show a response of the digital twin to pulse wave motion at an angle. And then I will discuss observed vibrations caused by passage of underground metro trains. So first, introduction of the seismic monitoring project. So it is building a skyscraper located in Yunnan province in its capital Kunming. It's a 50-story building with 4-story basement and on pile foundation that reaches 50 meters deep depth. It's a concrete steel construction. So resistance to lateral forces is provided by an integrated system of concrete shear walls and columns connected to RC coupling beams. And then there are 132 channels of acceleration. These are class B sensors, plus 6 channels of angular velocity. This is R2, angular velocity meter, and a 6-channel weather station. And then everything is connected. The purpose of this site was to provide data for research. So it has nothing to do with the government. University provided the money for me to do this. It's totally separate from the government projects. So it's supposed to serve as a full-scale testbed for studies of soil structure interaction and structural health monitoring and other studies. So let me then show it. So here, oh, I'm sorry. Okay. We see here the map of China. So my university is in Tianjin. It's very close to Beijing. It's a port city. And the building is located at the other end of China, diagonally, Yunnan province, which bounds. Okay, I'm trying to see that, but okay, maybe, yeah. Okay, so this slide shows the map of China, and the green rectangle shows the location of the university where my lab is, and the red dot shows Kunming, where the observation site is. It's there because there is high seismic activity. Yunnan province on the north, it is Sichuan, which is very seismically active. On the west is Burma. And it's in the diffuse zone of the collision of the Indian plate under the Euro-Asian plate. And this is in this band where there is some complex tectonic activity. And I've been fortunate to record earthquakes already in about 2.5 years of observation. This here shows a map of Kunming, actually a part of Kunming. It is by a lake. And the triangles here are stations of the Yunnan Strong Motion Network. They have about 250 plus stations in Yunnan, and about 50 are in Kunming. So that provides opportunity in future to study the arrival of waves that excite the building. Okay, so this is a Google map. This is the building. This is another building by the same owner. And I have colleagues in Yunnan Earthquake Agency, that's the government agency, local, that does everything, like the US Geological Survey in the United States there. So they found a building for me. Oh my God, sorry about this. Okay, so the building is pretty regular, rectangular. It's detached, which is fortunate because attachment of, let's say, shopping malls, etc., adds complication in the interpretation of the already complex real-life phenomena. And this here is Beijing Road, a busy street, under which there is a metro station. So there are a lot of vibrations from the traffic here. And also from the metro. Here is a metro station, maybe about 200 meters, from the building. And the metro goes about 15, 20 meters from the basement of the structure. Okay, so it has 50 stories, 4-story basement and piles. So this shows the vertical elevation, and then the location of the sensors. So the unique feature of this monitoring project is a dense instrumentation of the basement by triaxial accelerometers. We have 14 at 2 levels of the basement. And the purpose is to see how the basement and foundation deform, because the building is excited by seismic waves that go through the foundation to excite the building. And unique feature, even more rare maybe, or same rare, 2 boreholes arrays installed very near the basement. And they go down to a little bit less than 50 meters, where the tip of the pile foundation is. Okay, so the sensors are triaxial class B MEMS accelerometer made by Canterbury Seismic Instruments based in New Zealand. And the angular velocity meters are R2 by Ian Tech. That is a Lithuanian company that were adapted to be compatible with the recording system, so we get all data together, synchronized. And the weather station is Vaisala, is an industrial quality station made in Finland. So it's a truly international project. And we have a state-of-the-art network that...
Yeah, one question.
Yes.
Have you broadband instruments as well?
No, these are strong motion. And we record up to 100 hertz. That's the sampling rate. And effectively, it's really 85 because then the signal is conditioned already. So, but they are good enough, good enough. Okay, so this here shows the sensor network. So we have optical lines along 2 vertical lines going through the building. And certainly Ethernet lines from the optical lines coming to the sensor locally. And we have Ethernet lines and power over Ethernet supplying signal to the borehole sensors and the surface sensor. So the borehole have 1 surface sensor and 1 borehole, and there are 2 of them. And this is how the EQR120 looks like, and the R2 and the Vaisala. It's just about 36 centimeters long, very, very neat. Okay, so this here shows the structure. So the structure is actually shear walls, short shear walls that intersect each other, and the detail of the reinforcement is such that they form like a frame. And plus there is additional frame there. So at 48th floor, there is a roof, a glass roof on half of the building, and there are 3 more floors on the other half. So it's very flexible. So really the roof is 48th floor, this floor, where we have rotational sensor, and the other rotational sensor is in the basement, in the 4th basement here. So at every 10 floors, we have sensors along the diagonal. These are refuge floors that belong to the owner. The rest, this is a business building, so they have been sold to businesses. And we could put only instruments where the owner lattice, right? At the other, in between, at every 5 floors, there is a sensor at some distance here, so not at the diagonal. So we can get torsion, at every 5 floors. And this is the configuration in the basement. So this is the tower. So the tower goes from the 4th basement up, and it's surrounded by basement proper, which is a more flexible structure. Yeah, okay. So this here shows nicely the, oh my God, sorry. Okay, so the borehole is about 8.9 meters from the foundation, and the other one is only about 1.7 meters from the basement. Okay, and this is the metro is on this side. So we record the metro signal by the northwest borehole array. And important here is, oh my God. Okay, so this here is the aerial view, and this is an entrance to a parking structure. So the basement is a parking structure. So there is a lot of vehicle voice noise recorded by the northwest surface sensor. Okay, and this is a typical 5-minute record recorded in January, I believe, of 2021. The array became fully operational on 6th of January, 2021. So this is at about noon, so we see a lot of noise from elevators. This is the array in the center, okay, which is in an electric closet next to elevators. So a lot of noise there. And these here are the boreholes. This is the northwest borehole, and we see a passage of 2 trains. One is leaving the station, accelerating, the other one is deaccelerating. So I'll show later the signals in more detail. And this is the Fourier spectrum. So up to 10 hertz, we see the modes of the structure in which it responds as a whole. And then we see other peaks here between 35 and 50 hertz. And these, based on a model, right? These are vibration of the slabs. And we see other peaks there, which we don't know what they are, some local vibrations. This is the borehole that is on the other side of the building. We see frequency at about 2 hertz, 7 hertz, and we believe this is some construction site. And this here signal is the train. The train signal has equally spaced clusters of peaks, which are very intriguing. And these are the 3 components. This is longitudinal, transverse, and vertical. Okay. So now identification, first to see where our modes are, right? Using microtremors. The origin of microtremors are microseisms caused by ocean waves in the Indian Ocean, and also by waves in Lake Dianchi, which is very close. The closest point to the shore is only 5 kilometers. And they have been documented. Seismologists have studied actually the microseisms caused by the lake. Okay, and then we have very rich urban noise, as I mentioned. So initially in November 2018, we did an ambient vibration survey using mobile sensors, ETNAs, that my colleague borrowed us. And then we we again identified the building in 2021 using 1 hour of microtremor data stacked. And then we compare the results to see possible change due to deterioration of the building. And my student made an ETAPS model of the fixed base structure, which helped identify the modes, right? Interpret these modes. Okay, so these are results of the 2018 survey or campaign, right? How they call it in Mexico. We recorded actually microtremors at all locations where we have sensors, but there was construction work in the building, and we could use practically only the record at the 48th floor and at the basement, which were quiet. So we fitted uniform Timoshenko beam, and what we see here are impulse responses obtained by the convolution with the record at the 48th floor. One of the lines was obtained from the observed microtremors, and the other line is from the fitted model. And these here are transfer functions observed and of the fitted model. So from the ratio of frequency, we see that in the longitudinal direction, the building is practically like a shear beam, while bending is considerable in the transverse direction. These are the torsional peaks as well. And the Timoshenko beam model, it accounts both for bending deformation and shear deformation. And the wave propagation is dispersive. So from the dispersion theoretical of the fitted model, we get this phase velocity and group velocity for the dashed line, for the longitudinal direction and for the transfer direction. And the dots are just like velocity we get from the peaks, assuming that this is a shear beam locally. We fit a shear beam. So the velocity is about 400, 500 meters per second. And the fundamental mode is about less than actually maybe 0.3 hertz. Okay, for the transverse direction is 0.4 hertz, the fundamental mode. For the transverse direction is 0.28 hertz, so it's very flexible. And the torsional peak is at 0.39 hertz. So such low frequencies of the fundamental mode must have been excited by the microtremors, right? Regardless of the noise. Okay, so here we compare with the model, and actually the model was very, very useful. We could identify the vertical frequency, which we saw peak actually of the vertical motion near where the finite element model predicts it. These are the modes, you know, so I'm just going to skip them. You've seen many of them. And these are RMS values and peak values recorded along this central line. And we see that the boreholes are the busiest, actually, the busiest place down at 50 meters. Okay, and these are here RMS values and peak values recorded by the two rotational sensors. So we see that for the torsion only, we have amplification towards the roof caused by the building. Otherwise, actually, we have larger motion at the boreholes. I mean, in the basement than we have at the roof. Okay, so this here are Fourier spectra of the accelerations, x, y, z. X is in the longitudinal, y is in transverse, and z is up, and these are the rotational sensors. So we see clear peaks, and we see peaks even in the rotational sensors, and this peak corresponds to the lateral modes of vibration. And this is the torsion. So we could see 3 torsional peaks, actually. Okay, and these are the transfer functions in which we see clear peaks, and torsion is close to some of the lateral peaks, and the torsional actually sensor helped us identify, separate the torsional motion. And this is just by interpretation, first-hand analysis. We now use stochastic subspace identification method to find the modes. And these here are the vertical. And the vertical is actually very interesting because most buildings have only horizontal sensors. And if there are vertical sensors, they're only in the basement. And we identified the first vertical mode at about 3.2 hertz. These are also vertical modes, quite prominent. Why is this significant? Vertical motions are rarely even measured, right, or considered in design. They have smaller amplitudes, except near the earthquake, as compared to the horizontal motion, right? But that is true only sufficiently far from the earthquake. And another perception is that the vertical frequencies are very high, where the ground motion doesn't have much energy, but actually for such tall buildings, the vertical mode is at 3 hertz, the fundamental mode, which is where ground motion have actually energy. Okay. And this here, shows the peaks, so I'm going to go fast, and these are from 2021 data, the model impulse responses and the observed impulse responses. So from 1 hour ambient vibration data, we can get very, very nice shapes. And travel time is about ½ second from roof to the ground. And here we compare this with the results measured in 2018, and we see about 2.5%, up to 2.5% difference. For the torsion, maybe there is accuracy in reading, which contributes to these measurements. But these are differences that are of the order of magnitude of effects of weather, temperature, effects of nonlinearity, recoverable nonlinearity, depending on the amplitude of the response. And so we decided to study these effects, okay? And the weather in Kunming is mild because it's at 25 degrees latitude, but it's at 1,900 meters altitude. So the summers are not very hot, actually. The summers are the wet season. It rains heavily. And it's one of rare places I've been where one doesn't need air conditioning in July. And in winter, temperature rarely drops below 0 centigrade. So the springs have strong winds, and summers are very wet. So the climate is characterized by 2 distinct wet season and dry season. So we believe that the rainfall would have effect on the frequencies of vibration. So these are results from a paper that I just submitted for the World Conference next year. And we present preliminary results. We only analyze the east-west component in the first 4 modes. So we use stochastic subspace identification method to more precisely identify the frequencies because we look for very small changes. Okay. And we use data only from 2 sensors, simply to see first what we have. And then we'll do more detailed analysis. So there have been recorded probably around 30 earthquakes so far, 26 until last May. And 16 are kind of very nice records. But they were far. The largest one, a magnitude 6.4 at 300 kilometers. So at this stage of the analysis, we assume that all changes were caused by environmental and operating conditions. So this here shows the variation of the frequency, and there are obvious seasonal cycles. This is the first mode, first transfers, second, third, and the fourth mode. This shows the distribution of the values. So sigma over mu is the coefficient of variation of the observed values. And in the last column, sigma residual over mu is the coefficient of variation of the residuals. So we see the observation has about 1 to 2%, variation, and the fitted model has less variation. So we do correct to some degree. There are 3 tables because we did analysis for hourly values, for daily values, and for weekly values. And the scatter is much smaller for the daily and weekly values. But then if you want to take into account the effects during particular time of the day, we need to have good prediction for the daily effects. So this here, we consider temperature, W wind speed, U absolute humidity, which we get from the recorded relative humidity, and the rainfall intensity. So these are weather components that we consider. Okay, so here we see the temperature, the RMS value of acceleration at the 42nd floor, then the wind speed, the humidity, and this here is the rainfall intensity. So because the wind speed is related closely to the RMS value, we use the wind speed. And here we have a break in data after some storm. We were so focused on the boreholes and contacts, so that we forgot to monitor the health of the Vaisala station. Okay, and for the humidity, we see 2 populations, right? The wet season and the dry season. Okay, so we fitted a linear model, constant term, the wind speed linear, the T is the temperature linear, so all linear. And we see that the 3 tables are from hourly, daily, and weekly values. So we see here that the temperature coefficients are all negative, and by controlled experiments in narrow ranges of the weather parameters, we see that the frequency decays with temperature. This is very much dependent on the structure. Some have found increase of frequency with temperature, and this is for cracked structures. And the hypothesis is that the expansion of the material of the concrete closes the cracks and actually stiffens the structure. But this is a new building, and we see what could be expected from the properties of the material. Then we see that for the humidity, for the wind speed, also the coefficient is negative. So larger wind speed, right, lower frequency because larger amplitudes of response. This is a nonlinear elastic behavior. The coefficients are positive for the rainfall and humidity. For the rainfall, there is a hypothesis that I have actually shown on a model that produces effects of same magnitude as those observed in Millikan Library and other structures, which is increase of frequency by heavy rainfall caused by swelling of the soil, and could be explained by representing the soil as fully saturated poroelastic material. Okay, so we use this to correct. On the left-hand side, we see the daily values, and we see that we follow these values, but we don't quite match all the amplitudes. And we need to refine the model, maybe do some quadratic terms. We account for phase delay of the temperature effect, because we measure it outside, and it comes to be 20 hours, order of magnitude delay. These here are the daily values, and they don't look good except for the fourth mode. So for the fourth mode, with some refinement, I think we will be able to follow closely, to fit closely the observed variations, or to correct for the effects of the weather. Okay, so we think that in future we can actually get better results to correct for these effects. So why are these important? These are small changes, but if we want to use sensors to detect small damage and hidden damage and localized damage, they would produce small changes. So we need to know first if these changes are due to the weather, right? Or they are due to change of stiffness. And the prediction of this effect will actually improve the health monitoring using ambient data before the earthquake and ambient data after the earthquake. Okay, so let's see, what do we have? Okay, so changes are small in the prediction, reduces the scatter. So now observe the response during earthquakes. Okay, so these are epicenters of 16 earthquakes. This is the Yangbi earthquake sequence. The main shock was 6.4 magnitude. And I have animation here for the main event of Yangbi and for Shuangbai, which is a very nice, produced very nice record, broadband. So it's a magnitude 5.1 at about 80 kilometers, no, 100 kilometers. Okay, so let's see, I'm going to try. Now, how can I try? Oh, my animation doesn't show. Anyone knows how it can show? Yeah, this happened actually at a conference, and only some people knew how to solve it. Yeah. No, it doesn't show. Okay. There is something is. Let's see what to do it. Needs an IT expert. Oh, did you do? Wow. Okay, yes. So I should be able then to play it, right? Oh. So how do I turn it on? It's coming? Okay. So this is all observed. The nodes are where we have sensors. The planes are obtained by interpolation, bilinear, I believe, interpolation. And my student could actually extrapolate a plane at the top, but he said it didn't look good with such exaggeration. So at the top we record the rotation as well, okay? And we see here the particle motion at the surface sensors and at the borehole. And we see some kind of a complex elliptical motion, but doesn't look like a theoretical prograde Rayleigh wave. Rayleigh wave ellipse. Huh? Signature, yeah. And this is not free field motion. Actually, doing the convolution of the signal at the surface and at the borehole has only acausal waves, no causal wave, because the structure is so close. Okay, so this is exaggerated, but you see, it looks like pretty scary and one gets nauseous. It is exaggerated, of course. But we can see how it deforms and how it may deform, during larger motion. Actually, there has been magnitude 7.2 recorded not too far from the building. And the building is torsionally flexible. So the first torsional mode is has lower frequency than the transverse mode. So a lot of torsion. And I think this is interesting that we see the building moving vertically as well. Okay, so how do I get out of here? Oh, I have another one. So I want to run this one. Okay, double click on that one. No, just say yes. Right? Okay. Yeah. Okay, so this is Shuangbai, 102 kilometers away, magnitude 5.1. This one has more high frequency, high frequencies. And the arrows here show the direction of arrival of the waves. And we have an earthquake at 10 kilometers, epicentral distance, magnitude 2.1, beautiful signal.
Vertical motion is back. The bottom?
The bottom is the vertical, right? B4Z. This is in the basement, lower basement. Okay, so can you please put it back? I think now it's not so interesting. Okay. So next is observed rotation during earthquakes. And this is from a paper, invited paper for the keynote lecture of the rotational seismology and engineering application session at the World Conference of Earthquake Engineering next year. Okay, let's see. So motion of infinitesimal element of soil is described fully by 6 degrees of freedom. Is 6 degrees of freedom, described by 3 rotations and 3 translations. We record only the translations mostly because their magnitude is much larger, right, than the rotations. But the rotations are not insignificant in the near field of an earthquake, and they may contribute actually to damage and maybe even collapse of a structure. So it's good to know what these motions are as excitation and then how they affect the structure. And there is a working group on rotational seismology and engineering application, and Heiner Eagle is the leader from the geophysics side. And I'm a founding member, but haven't done much until now recently, that I have my own records. Okay, so they are not negligible in the near field of an earthquake, and there are papers of observed rotations. Our rotations are, of course, small. So let's see. What do I have here? Okay, so these are the rotations in time. Psi, X, these are rotational velocities as they are recorded, right? Instrument corrected. And at the 4th basement and at the 48th floor. And this is the X component, which is the north-south rocking. And this is the east-west rocking, in which the building is stiffer and it behaves like a shear beam, while in this direction it behaves like Timoshenko beam. So this here motion is the rotation of the floor slab, basically, because the building as a whole bends. And it doesn't do that or that much in the other direction. And this here is the torsion, so we see large amplification actually of the torsion inside the building. And these are the modes of vibration, right, of the lateral motion. And we see them also in the basement, right? And the reason for this is the fact that the basement doesn't move as the soil, as the incident motion, but is affected by the response of the structure, and the mechanism is the soil structure interaction. So we see these peaks, you know, in the basement motion. We don't see it as the torsion, so the input torsion is really small, but the rocking actually is more significant. And this is the Yangbi earthquake, magnitude 6.4, that produced the largest response. Okay, so here we see correlation, you know, seismology is plotted of the rocking angle and the peak particle velocities, vertical velocity, and peak rocking angle, which is the blue lines. And then the red dots and the fitted line show the correlation of the peak torsional angle versus peak horizontal velocities. Okay, and we see this linear trend as observed by seismologists. And this here shows the correlation of the motion at the roof, 48th floor, and at the basement. And we see kind of linear correlation. And we see very large amplification for the torsional motion because this is a torsionally flexible structure. So this here shows on the x-axis is the point rotation recorded by the rotational sensor, and it's the angle. And on the vertical axis is the chord rotation computed from the linear motions at the corners of the tower in the basement. So what do we see here? So we see that for the rocking angles, which are the first two columns, okay, show a rocking X component, a rocking Y component, and this is the torsion. And the rows correspond to disjoint frequency bands. Each band has one mode of vibration. So this just to see how with frequency this varies. And we see for the torsion, really almost they are along a straight line, except for the higher mode, of course, the fourth mode. And for the rocking motion here, we see that the point rotations are larger than the chord rotations, okay? So the fitted line goes like that. And what does that mean? This can be explained by the nature of the deformation of the floor slabs because they are very stiff in their own plane, you know. For torsion, we get point rotation is like the chord rotation, but the slabs are flexible vertically. So this instrument in the middle, it records actually local deformations of the slab or of the joint actually, near which it is located. And why is this result significant is that we should use with care the rotational records because they record something very local if we want to get the torsion. So if we are interested in rocking of the structure as a whole, we should use chord rotations and point rotation if we are interested in local rotation of the joints. And it would be nice to have such sensors at every joint, right? But we cannot. So this here is a snapshot of an animation that my student made. It's a half-sine pulse exciting the building as a plane wave at 45 degrees incident angle. And it shows, and the model is very realistic, right? The basement is flexible. First, structural engineers soil is rigid, and the structure is excited as the free field motion. Then people who do soil structure interaction, boundary element method, they assume that the foundation is rigid, right? So it just moves as a rigid body, and that makes it manageable, actually, with limited computing resources. But now we have kind of faster computers. So this here is a realistic finite element model in which the foundation actually deforms. And this is exaggerated, of course, so we see the pile foundation deforms and the basement deforms. So, and this is a moment when the basement warps, you know. So what do we see here? We see that wave starts going up at velocity about 420 meters per second. And this is just beginning, so it still hasn't reached the top, but the top is actually deformed. And why is it deformed? Because of these vertical motions at different points, or the vertical motion at different ends, actually. And because the building is very stiff, those waves propagate practically instantaneously to the top, right? So the horizontal deformation, it takes time, half a second to propagate, but the vertical propagate instantaneously. And there are vertical drifts here that we believe should be investigated, and because they may add to the horizontal drifts and may, for a structure that is weakened during nonlinear response, may lead to collapse, actually, progressive collapse. So that's about it. Next, digital twin. So my very able student made a finite element model of the soil, 540 meters by 300 meters and 100 meters depth. We have a borehole up to 100 meters at 29 locations just under the building and around the building. So we have site-specific profile of the soil up to 100 meters depth. I have no idea what's underneath. So every pile is modeled separately. We consider two variants, one with bond contact and one with a friction contact. Friction contact, it only works on pressure. Soil works only on pressure and not in tension. And friction provides like constitutive law of the relative motion of the soil in the structure. So we have results for both models. And I got a project to study the role of flexibility of foundation in the response of tall building. So my student made models, one fixed basement, another one that is no piles, and it has flexible foundation. No piles and rigid foundation. So this is the assumption in boundary element models, right? Rigid foundation and no piles. And then flexible foundation, no piles, and then the full model, which is flexible foundation and on piles. And this here shows plot how the fundamental frequency changes. This is for the bond contact, and this is for the friction contact, so much more reduction, actually, for the friction contact. And this here is the full model, is at the end. So we see about 14% reduction, actually. We account for caused by soil structure interaction. This here is the damping. The damping increases, due to the soil. And this here drifts. So I'm going to go fast because I have many slides. This here is the base shear and overturning moment. So basically the idea here is to see how the response depends on our assumption on the model. Okay. And next I have again simulation. Can I please have your help? So the building is excited by a half sine wave pulse arriving at 45 degrees.
First.
Yeah, the first one, then second and third. Oh, so I cannot control, or I can control here.
Control the...
I mean the cursor to go slowly. Okay, so you can slide it slowly. So this is an SH wave. Just slide the time from the left. No, he can't see it. It's such an angle.
Okay, yeah.
Okay. So the pulse goes very quickly, but the building vibrates long after the pulse is gone. And this kind of motion excites the torsion. Now the second one. The second is a P wave, so it imposes vertical displacements and also horizontal displacements, okay? And it actually warps the foundation. So that was a snapshot from this kind of motion. Okay, so. And we can see actually, if this goes slowly, how the wave goes up, reflects, goes down, and then bounces back and forth.
This is P wave?
That was P wave. Would you like to see it again?
Yes, please.
Okay, so the P wave, and I can slide it slowly, since I can see it there. You can use actually even the cursor. And my student wrote a MATLAB code that actually plots this rather than using commercial post-processing software. And he can edit them. The files are much smaller. So he's a very, very able student for computation and technology. Okay, shall we do the SV? Okay. And I can show it to you after, Paco. Who is interested? Okay, so 5 o'clock. Okay, so this is the SV wave, but I think that the P wave is actually kind of neat. And this could be a pulse of near field ground motion, right? Very near the earthquake. Okay, I can, actually these are on YouTube. I started a YouTube channel. Okay, I think we can continue and I can send you link or even copy the files for you. Okay, so this was the model that generated that. So what is this? Okay, now observed vibrations caused by the passage of underground metro trains. As I mentioned before, the metro goes under Beijing Road, and our borehole is very, very near, actually. We don't know exactly where it goes, but supposedly goes in the middle. This is again the location of the sensors where we see the train passage. This here is a time frequency plot of over 24-hour period. We see the train comes at about 6 o'clock, 6:30. Because China is a one time zone, people in the western part, they actually start their life 2 hours later than the people in the east. So this is very early, even 7. People go to work at 9. Okay, so these lines are actually passage of trains. And we see these are not continuous lines, and that's because the spectrum has very peculiar peaks. And this here is the 50 hertz frequency that the borehole sensors, underground is a very busy place with lines because of the metro, etc. This is 24 hours. So we see weak lines and strong lines. The weak lines are the slowing down metro. because there is less force exerted by the wheels, so it's a weaker line, and the strong lines are the accelerating train. So the frequency is really between 35, hertz and up, and this here is the borehole. So the borehole gets no noise from the surface. So it's pretty quiet if we want to observe the train. This here is the passage of this accelerating train, okay? So this is maybe, I don't know, two minutes time frequency map. That was at the borehole, and this here is at the surface. So this here are local vibrations and a lot of local noise, actually, caused by vehicles coming to the parking structure. And this shows these trains. This was the Voila, actually, record where I saw the trains. So I like to show it. It's very early in January, just when the array became operational. So we see here that the slab vibration is actually similar frequencies as the train. And at the borehole, it's very close to that slab where vehicles go around the building. So it records these vibrations as well. Okay, so this here is the combined signal. Two trains, the top is on the surface, right? And the bottom one is at the boreholes. So we see the two trains, the whole signal, everything. And we see much larger amplitudes near the surface. This here is that 5-minute record, less the passage of the two trains. We see still large motion, okay? And this here is the passage of the accelerating train. So this is the vertical, which is actually of primary concern, but sometimes it's useful to look at the horizontal ones. So at the borehole, the vertical has largest amplitude, larger amplitude than the horizontal ones, but at the surface, the horizontal ones have larger amplitude because of the amplification near the surface, the free surface effect. And these here are the peaks. We see, like equally spaced clusters of peaks, okay, which are intriguing. And this is a record in the basement at the corner, which kind of filters nicely these high frequencies. So we can measure nicely the clusters. So these large peaks are exactly at 5.22 hertz. There are smaller peaks at about 2.6 hertz, I believe. So there are different kind of, I think these are different superimposed effects. And what causes this? The 5.2 hertz can be explained by the action of this boogie. So each car, these are passenger cars, has two bogies in front and in the back, and every bogie has two axles and a pair of wheels, right? So the action in time of the passage of these two wheels can be explained by this frequency. And the other frequency, the smaller distance, by, I think, maybe this pair of bogies. So my student made a model, actually, to try to explain this, these peaks. And actually, he was in love with seismic metamaterials. And he came to study that with me. And I just told him, if these seismic metamaterials are not going to work for wave coming, vertically. So for earthquakes is, it's a very nice problem, but the effectiveness is really limited to horizontally propagating waves. But for trains, actually, for train traffic, they would work because these are high frequency waves. The source is near the surface. So he put barriers as well, but I didn't put results here to show them. So this here shows the attenuation with distance relative to the surface sensor, because we don't know what is at the metro and even exactly how far it is. So we see very rapidly. So this is the normal distance from this borehole. So we see the first point is this one, second, third, fourth, fifth sensor. So these are along the X direction. We see very rapidly this attenuate in the basement. And of course, this is just a metro train. For high-speed trains, these are large forces felt at 300 meters. And seismologists are very interested actually in trains. I'm reading Humming trains papers because they use them as sources of high frequencies near the surface in tomography. So the train was a bonus, right? I mean, I was not asking for a train, but it happened that there was a train. So this is his model. And then if he's interested in points below the tunnel to make his model smaller, he puts transparent boundary on the top to make full space. Or he puts transparent boundary just not too far from the bottom of the tunnel and puts free space here. He models the track very realistically and models this slab here realistically. This here area that is between the slab and the tunnel, that one can act as absorber, but he may use zero element that directly transmits the force because there is a lot to learn. So this is the train signal. So the passage of each wheel is modeled as a triangular signal. And there are 3 passenger cars and there are engine cars at both ends. And this is what he gets for the time at one of these points. And this is the spectrum. So he gets clusters of peaks, but then there are different forces here. There are forces due to imperfection of the track and of the wheels, which he doesn't model. There are also dynamic forces due to the slipper, and we need to learn actually about it. It's a whole profession, you know, that studies this. And he used the model only for the quasi-static force exerted by the weight of the wheel, and which is a moving load, right, with certain action. So this is at another location. And acknowledgements, actually, I am exceeding the time. So I would like to thank the Tianjin University who gave me money to do my dream seismic monitoring site. And also to National Natural Sciences Foundation of China that provided me with a grant to do the modeling, finite element, and analysis of the effects of the flexibility of the foundation in the response. And I want to thank my colleagues from the Yunnan Earthquake Agency, Ling Guoliang, and his doctor now, actually, I should add this, and Dr. Jiawen Cui, who actually arranged everything for me to get permission to install this, and Lin goes to the site to do troubleshooting. So we don't have to fly, you know, for 3.5 hours. It's a direct flight between Tianjin and Kunming. And I want to thank my very able and hardworking students who produced the results that I showed today. So, oh, and these are some papers. So we don't have many papers, actually. A lot of these are new results, unpublished, and I have them all nice, and I'm writing papers, actually. Putting together, doing my part for the papers. Okay, thank you for staying. Another topic that I work on is seismic hazard. So I got records from 2008 to 2018, recorded by the Yunnan Strong Motion Network. And we've studied with the student the source parameters, the attenuation of spectra and peak values, and now duration. I have another student who is doing master thesis on duration, and a PhD student who would eventually do hazard, hopefully. So that's my full-scale laboratory from Los Angeles. I moved it in Yunnan, you know. Thank you.
Maria, very nice. Congratulations for such a nice account of your experience with this Yunnan or Hunan building. It's magnificent work with a lot of data. I was wondering, how do you handle all this information with thanks to your students? I have few questions. Have you an assessment of how much it cost to make the experiment?
You mean
the budget
for the deployment?
Deployment and students' budget.
I mean, many
salaries.
Academy spaces. I believe that for the sensors, I paid 200,000. Pretty much, just a little bit over or a little bit under. And the installation, drilling of the boreholes, I forgot.
Yeah.
I think it's about $14,000 because I think in dollars. But in RMB, you can do a lot, actually, because labor is cheap. The Huawei network switches, they are cheaper than Cisco, right? And they are very good. We put firewall there. Actually, the site was hacked within a month from the time it got operating. And we had static IP line, and maybe someone thought it was a bank or something. Why would it have a static IP line? The wiring of the building was like peanuts compared to what it is in Yunnan. So first, the cables are optical cables made in China, Ethernet cables, CATS C86 made in China. And the labor, very reasonable, right? But I don't remember now how much it was.
So did you were able, I have another two questions, very little questions. Were you able to find or to look some nonlinear behavior?
No.
Okay, it was just very small.
These are small motions, but you know, this was for research. Nonlinear behavior gets us in trouble, you know.
Yeah.
I don't even have a nonlinear model. I have a new PhD student who will make a nonlinear model. And I have one very good from Iran. He will make nonlinear model of the soil. So, you know, eventually we'll have, maybe there will be a big earthquake, you know.
Okay. So. And another question finally, for the train cases, have you had the chance to talk with the operators of the system to have the running of only one car instead of the full train?
No, I mean, this is something very recent, actually. The student produced results, is writing his thesis, which I'm supposed to get at the end of the week and comment first time on it. And I don't speak the language, and the trains are something out of my main interest, okay. Right? And I need to write papers. Student needs papers to graduate. In China, student cannot get PhD without at least two papers in high impact factor journals, and preferably more, you know, and they have more actually.
That's
more
we
than
want
3
here as well.
Also?
We want that.
You want that. But at USC, it's not. It's not required.
We're changing, we're lessening the standards. Thank you very much. Congratulations, Maria. It's very nice.
Thank you, Paco.
Okay.
Thank you very much for your talk. It was very interesting. I just want to know about the range of the accelerographs that you install in the building.
What about them?
The range. I mean, what is the maximum acceleration that these accelerographs are capable of measure?
Mm-hmm. I can. The range. The range is plus minus 3G.
3G.
3G. Yeah.
Okay.
And the first batch of 8 were plus minus 5G, but we took them out and replaced by 3G. I have about 15 spares actually in the lab for ambient vibration. And we've compared them with an Etna because from all of the sensors plus 15 spares, only 2 were faulty. And the fault was, I guess, difficult to detect. One capacitor was switched, so it produced extra damping. But the phase was accurate. And then we put Etna and also 2 of these EQR 120 to find the correction of the amplitude. And we corrected that actually for the amplitude. So even for ambient vibrations, half an hour record, we could pull out the peaks with at very low frequency, 0.26 hertz, and for the earthquakes, we have beta signal to noise ratio, right? So we record the first mode very well. So the philosophy of putting Class B instruments is to achieve a spatial density, higher spatial density of recording, because we could buy about maybe 3 times, 2.5 times more sensors than if we put Etnas. Actually, even much higher factor, because buying Etnas through their representative is a rip-off. While from New Zealand, my university imported the sensors, and at a 2%, interest to the trading company. So suppose we have a building, and it's a complex structure, and we have very few very accurate sensors. So we know very accurately how these few points move, but in between, we don't know. It will be different, right? So here, the idea was to put more sensors to get spatial resolution. And actually, the verticals are very interesting, that we could put vertical at all of these points was very valuable for research, and it's rare. I'm sure there are buildings that have it. In Japan, in US, no, none of the buildings have actually verticals, not even the densely instrumented. Millikan Library and the Factor building. Yeah. Okay.
Well, so far, what is the largest acceleration that have you recorded?
I don't know by heart. It was that earthquake. I had tables. Yeah, actually, it should show in some of these points here. Okay, here. So these are peak accelerations. Okay, times 10 to minus 3 centimeters per second, and the largest one is about 5. Yeah. And these are the rotations on this side. Rotational velocities should be. And these should be accelerations, I believe. Oh no, these are angles, and these are velocities.
Yeah.
Okay, centimeters per second. So I don't remember by that. But small,
Yeah, thank you.
Thank you very much, Maria, for your talk. We finally, we appreciate you come back to ATUNAM, to the Institute, and the Instituto de Ingeniería is have this presence for you. Thank you very much.
Thank you for your interest, staying to the end. Thank you, Marco. Oh, my goodness. Or diploma, certificate. Thank you very much.
Gracias por venir.
No, pero más, es denso.